All right, greetings YouTube, beautiful mind here. All right, so this will serve as the lecture for, this is going to be what? This is week 4, Wednesday for applied statistics. We're going to be doing section 4.2 binomial distributions. A quick update for our students. I hope everyone is doing well. I want you to be aware that exam 2 is available on Pearson. It's due this Saturday at 11:59 p.m. You get unlimited attempts until the deadline. Past the deadline, you still get unlimited attempts. You can actually work on it past the deadline, but it'll be a late penalty. So past the deadline, the highest you can make is a 79%. Other major announcement that we need to be aware of: there is a participation and honesty quiz available on Moodle that needs to be submitted as soon as possible as well. If so, those are the main 2 items. I can't think of anything else. If you have questions or concerns of anything, you have to write them down. You have to email me and reach out to me. I feel like I'm good about responding to questions and emails and inquiries. So like when I see them, I try to make it a point to respond to those, each one. Okay. I can't think of anything else. So we're just going to move into the presentation for today. So again, we're going to continue chapter 4, discrete probability distributions, and today we're going to be doing section 4.2, binomial distributions. When you look at that term binomial, what does bi mean to you? What does the prefix bi mean to you? Bi, in this context, means 2. I think nomial is like a term, something like that, or name, but 2 terms. Polynomial, binomial, yeah, 2 terms, right? So binomial distributions has something about 2 going on. So let's see what's going on. Okay, so some objectives here: how to determine whether a probability experiment is a binomial experiment, how to find binomial probabilities using the binomial probability formula, how to find binomial probabilities using technology, formulas, and binomial probability table, how to construct and graph a binomial distribution, how to find the mean, variance, and standard deviation of a binomial probability distribution. So a binomial experiment, the experiment is repeated for, so these are conditions for it to be a binomial experiment. The experiment is repeated for a fixed number of trials where each trial is independent of other trials. Okay, there are only 2 possible outcomes of interest for each trial. The outcomes can be classified as either a success or a failure. Okay, the probability of success, P of S, is going to be the same for each trial, and the random variable X counts the number of successful trials. Okay. Here's some notation. Let me see. Can I go like this? That's not really helping. I think I have a way of doing that. I just got to think about how to get it to look like that. But that's okay. I'm just trying to think of how I can get it to display differently so that we don't have all the extra stuff on the edges. I think I have a way of doing it, but I'll get that going on the next one. So some of the notation are: N is going to be the number of trials, the number of times each trial is repeated. P is going to be the probability of success. Q is the probability of failure, which is 1 minus the probability of success. And then the random variable X is going to be the count of number of successes in N trials. Okay, let's look at this example. Okay, we're going to leave it like this. So we're asked to decide whether each experiment is a binomial experiment. If it is, specify the value of N, P, and Q. And list the possible values of the random variable X. If it is not, explain why. Okay. So here we have a certain surgical procedure has an 85% chance of success. A doctor performs a procedure on 8 patients. The random variable represents the number of successful surgeries. So the first condition, let's see, the experiment is repeated for a fixed number of trials with each trial. So how many times is this trial repeated? This trial is repeated 8 times, right? Because he does the operation on 8 patients. Second condition, there are only 2 possible outcomes, either success or failure. And again, keep in mind that each trial is independent of each other. So one surgery does not affect the outcome of the next surgery, right? Each trial only has 1 or 2 outcomes, either success or failure. All right, so either the surgery is successful or the surgery is not. Okay. The probability of success is going to be the same for each trial. So for each trial, the probability of a successful surgery is about 85%. And the last part, the random variable X counts the number of successful trials. Yeah. So this one, this is an example of an experiment that is a binomial experiment. Again, each surgery represents a trial. There are 8 surgeries, and each one is independent of each other. There are only 2 possible outcomes for each surgery, either success or failure. The probability of success is 85% for each surgery, and the random variable X counts the number of successful surgeries. So that would be considered a binomial experiment. Oh, I forgot to end. Okay, well, we have it here. So N is going to be the number of trials. So it's 8 trials. Probability of success, P, is 85. The failure is going to be 1 minus P, which is going to be 15%. And then the random variable X, counting the number of successful surgeries that we can have, we could either have 0 successful surgeries or 1 successful surgeries or 2 or 3 or all the way up until we get to 8 successful surgeries. Okay, let's give this one a go. Again, we're asked to decide whether this experiment is a binomial experiment. If it is, identify the values of NP and Q and list the possible values of the random variable X. If it's not, explain why. A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. We randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Okay. So one thing is, okay, so if random variable X represents the number of red marbles, what's the least number of red marbles that we could have? We could have 0 or 1 or 2 or 3. What does the trial look like? Let me think about it. Oh, so we're choosing 3 marbles, right? So what's the probability of getting a red marble here? How many red marbles do we have? We have 5 red marbles out of a total of, what is it, 5, 9, and 6. So let's see, 5 and 9 is 14, so 20. So then so the probability of getting a red marble on the first trial is what? 25%. So say we get a red marble on the first trial, when we go to do the second trial, if we choose a red marble on the first trial, on the second trial, the probability of getting red is going to be what? 4 out of 19, which is not the same. In either case, whether we get a red or not, the probability changes for the second trial. Remember that the probability is supposed to be consistent. The probability of success is supposed to be the same for each trial, and in this case, each trial does not have the same probability of getting a red, mainly because we're doing this without replacement. So this is not a binomial experiment. The probability of selecting a red marble on the first trial is 5 out of 20. Because the marble is not replaced, the probability of getting a red on the second trial is no longer 5 out of 20. So the trials are not independent, and the probability of success is not the same for each trial. So this is not a binomial experiment. Okay. So we have this binomial probability formula. Let's see, right here. This is a combination n choose x. So n objects chosen x at a time. So it's just a combination formula. You see it here. So again, n factorial, for instance, if we did 5 factorial means 5 times 4 times 3 times 2 times 1. Say it were 3 factorial. This exclamation mark means factorial. 3 factorial means 3 times 2 times 1. So factorial just means take that number times the previous number times the previous, and keep following that pattern until you get to 1. Okay, P here is the probability of success. X is the number of successful trials. Q is the probability of failure. And then you have this N minus Q. Okay. Number of failures is N minus X. Okay. Let's give this one a go. So it says rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. Okay. Let's see. So, and let's go like this. Paper. I like it like this. So if this were binomial, right? I usually like to write my binomial formula in the following way. We're going to say n choose x times the probability of success to the power of the number of successful trials times the probability of failures to the power of the number of failures. Okay. So this n choose x, that's just the binomial coefficient. That means ncx. So let's see. If this were binomial, what's our n? How many trials are we doing? 3 patients, right? So in this case, I can go here, I guess. Our n is 3. How many, what's the probability of success? Probability of success is 90%, so we're going to say 0.9. The probability of failure is 10%. And what do the x's look like? Find the probability of surgery. Exactly 2 patients. In this case, our x is 2. We want the probability of x being 2. Okay. I just want to take this. I'm going to move it here. Because here is fine. Okay. Let me see. So we're talking about surgery. So, okay, let's just kind of go ahead. So let's calculate the probability. So we want to find, so we have identified this as binomial. We want to find the probability of x being equal to 2. So how many trials? We have 3 trials. So we want to do 3 choose 2. That's called the binomial coefficient. Times the probability of success. It has a 90% chance of success, and this occurs in this case. We want 2 of the surgeries to be successful. Times the probability of failure is going to be 10%, and this occurs once. It's going to be 3 minus 2, which is going to be a 1 there, right? So then we just crunch this number. Okay. So the way I like to do combination, so 3 choose 2. A combination, I like to calculate it this way. So that formula that you saw with the n factorial and all that, it's actually the same as npr over r factorial, right? Let me see. If we said 9 times 9 is 81, so that's going to be 0.81 times 0.1. Okay. So then npr, so just means 3p2. We're gonna, it's like 3 times 2 times 1, but instead of going out 3 spaces, we only go out 2. So 3 here, let me change it to like this. This means this is the same as 3p2 over 2 factorial, right? So ncr is the same as npr divided by r factorial. So 3p2 just means 3 times 2. Instead of going all the way to 1, we only go out 2 spaces. Divided by 2 factorial is 2 times 1. Okay. 0.1 times 0.81 is 0.081. It gets smaller, right? The 2's cancel, and then we're going to say 3 times that number. So we get a 3. 8 times 3 is 4. Get rid of the 2. 2. And then the decimal goes here. You can use a calculator. I just wanted to give it a go by hand. Okay. All right. Let's see. How do we do? So let's see. To answer the question, it says find the probability of the surgery being successful on exactly 2 patients. All right. And we would, and that this result makes sense because if he's doing a surgery and he has a 90% chance of success, you don't want the surgery to be successful on exactly 2. We want the surgery to be successful on all 3. So since it has a high chance of success, any other outcome should have a low probability. Sorry about that. I'm just waking up. Okay, so let's see how do we do. Oh yeah, they use a tree diagram. That's fine. So the first surgery could either be successful or a failure. The second surgery, the first surgery is success. The second surgery is also success or failure, or this is also success or failure, right? So we have this tree diagram. So then the outcomes could be the first is success, second is success, third success. So this one has 3 successes, and the probability is here. We multiply those. So we're only concerned with the ones where we have exactly 2 successes. And you see the same result here. Okay. So where we use the formula, they use a tree diagram. The tree diagram is fine, but then when you start to deal with like higher cases, like say you had 7 successful trials, you don't want to do a tree diagram going 7 branches deep or whatever. Okay. But they got the same 0.243, and you see it there. So then the method 2 was using a binomial probability formula, and this is what we just did, and you see it here, and you see the numbers matching up. Okay. So for a binomial probability distribution, list the possible values of x with the corresponding probabilities. Example, binomial probability distribution for microfracture knee surgery. If we had 3 surgeries and the probability of success is 75%. Then for a binomial distribution, we have the possible outcomes with the corresponding binomial probabilities. Okay. So in a survey, U.S. adults were asked to identify which social media platform they use. The results are shown in the figure. 6 adults who participated in the survey are randomly selected and asked whether they use a social media platform. Facebook. Construct a binomial probability distribution for the number of adults who responded yes. Okay. So not that one. So let's see. So if this, let's go here. If this is a binomial distribution, what's our n? How many trials are we talking here? Okay, so this survey was conducted for six adults. What's the probability of success? So for them using Facebook, if we look at the chart, it says 68%. So the probability of success is 68%. So then what's the probability of failure? 32%, right? Because if that was 70, there would be 30 plus the additional 2 that we knocked off. And then X can take on the form of what? 0 through 6. So the possible outcomes, we could either have 0 people say yes, or 1 person could say yes, or 2. Notice that each trial, each person can either say a yes or no, and it doesn't affect, it's independent of the next person, right? So X is going to be the number of successful trials. We could either have 0 people say yes, or 1 person say yes, or 2, or 3, or 4, or 5, or 6. Okay. I'll do this one by hand. I say that because I'm tempted to use like some technology, but I'll do one more by hand, and then from then on, I'll probably start using technology. Okay. All right. So again, the binomial formula, we're going to say n choose x times probability of success p to the value of x to the power of x times q to the power of n minus x. Okay, and this is for each x. This is the probability p of x, right? Okay. I really don't want to do this by hand. Like if we were in class, I totally would delegate this one. I would count the number of students and like, okay, let me get 7 volunteers, and I would distribute it out because this was just a little bit long. But let's go ahead and write it out. So let's start off with the probability that x is equal to 0. All right. So our n is 6, so we're going to say 6 choose 0. Probability of success was 68% to the power of 0, and the probability of failure is 32%. In this case, to the power of 6. Right? 6 choose 0 is 1. I want you to make a note that 0 factorial is, by definition, is 1. Anything to the power of 0 is also 1. And then we just need to find 0.32 to the power of 6. So I'm going to open up my calculator. I am going to use the calculator a little bit. I'm not going to, because actually you could type a lot of this in and it'll automatically spit out pretty much all of it. You can even use Excel or numbers if you're on a Mac. I'm just going to load my calculator and share it. Okay, I think it looks healthy. Okay, so then we're going to do 0.32 to the power of 6. Let's see. And that's approximately 001. I'm going to do 737. Okay. All right. Let's go ahead and do so that's the probability that x is equal to 0. I'm probably going to need another page. Let's go ahead and do the next one, the probability that x is equal to 1. So the probability that x is equal to 1, again, that's going to be 6 choose 1 times the 68 to the power of 1 times the 32 to the power of now 5. 6 choose 1 is just 6. I'm just skipping the formulas because I already know these. Like 0 and 1, like n choose 0 is typically 1, n choose 1 is just n, and then the rest I usually calculate. So just for the sake of time, I'm just doing a shortcut. Let's see. So then that one is going to be 6 times the 68%, and then times this 32 to the power of 5. Okay. Okay, so we're just going to say, 6 times 0.68, nope, 68 times 0.32 to the power of 5. Okay, and this is approximately, I'm trying not, I don't want to round, I'm trying to take it out to the long decimals. I try not to round it to the very end. The earlier we round, the more it kind of skews our data. So let's see, 36, 9, I'm gonna do 902. That's fine. Okay. All right, hopefully this should be okay. Let's calculate the probability that x is equal to 2. That's going to be 6 choose 2, 0.68 squared times 0.32 to the power of, what is that now, 4. Okay, you should notice a pattern by now. Let's calculate 6 choose 2. So this is going to be equal to, now 6 choose 2 is going to be the same as 6p2 over 2 factorial, okay? I'm just going to use a calculator for, honestly you can use a calculator for a lot of this, but 6.8 squared and 0.32 squared. So 6p2 means instead of going 6 times 5 times 4 all the way down to 1, we start at 6 but we only go out 2 spaces. So it's going to be 6 times 5 over 2 times 1. This turns this into a 3. Okay. So then ultimately that's going to be what? 15. 15 times 68% squared, 32% to the power of 4. Okay. I'm just going to just use the calculator instead of showing it. Well, it doesn't matter. Let's be consistent. Okay. So then this is going to be, let's see, 15 times 0.68 squared, 0.32 to the power of 4. Okay. That's totally not a 4. Delete. I think this is okay. So again, we get approximately 07, 27, let's do 29. Okay. On our way, almost there. So then the probability that x equals 3, 6 choose 3. Now again, there are faster ways of doing this. I'm just doing this for introductory purposes, but there are like way faster ways that you can use. 0.32 cubed, right? So again, 6 choose 3 is going to be 6p3 over 3 factorial, and then the rest 68 cubed. Like honestly, you can put in the combination in your calculator as well. Okay, so instead of, well, let me do this one because I just want you to see it. 6p3 means 6 times 5 times 4. 3 factorial means 3 times 2 times 1. This cancels this. That turns that into a 20. 68 cubed. 32 cubed. Okay. Go ahead and add a page. Okay. So just to show you, for instance, in this calculator, if I wanted to do 6 choose 3, let's see. If I go over to, I think it's in stat, calculate. No. Let's go to math. The far right is probability, so I'm going to hit the left button. And number 3 for combination. So for instance, this one we just did 6 choose 3. So I'm going to hit 6 NCR3. And the answer should be 20. All right. Okay. So I'm just going to type, I guess I can just type it in. So then it's going to be 20 times 0.68 to the power of 3 times 0.32 to the power of 3. Okay. So then this one is 0. Let me see, we got 206,066. Okay, that's an approximation. Let's go ahead and calculate the I'm going to start using some shortcuts now. Probability at x is equal to 4. That's going to be 6 choose 4. That one should also be 20, I think. Let's see. No, it's odd. There might be one more. But we're going to, let's keep it going. 0.68. This will probably be the last one I do by hand. Nope, not 3. To the power of 4 times 0.32 squared, right? So 6 choose 4, what that means is 6p4 over 4 factorial. The rest of these I'm going to use my calculator. Okay. 6p4 means 6 times 5 times 4 times 3. We went out 4 spaces over 4, 3, 2, 1. Right? Let's see. The 4 and the 3 cancels the 4 and the 3. The 2 turns the 6 into a 3. So that's really just 15. 68 to the power of 4. 32 squared. Okay. I want to check it really quickly. So if we did 6 math probability number 3, 6 choose 4, the answer should be 15. Okay. So then we're going to do 15 times, or to the power of, times 0.68 to the power of 4 times 0.32 squared. Okay. There's a faster way than, even with the combination, there's even a faster way. This is approximately 0.328418. Okay. I'll do the fastest way. Well, another way. There's at least, I can think of at least 2 more ways of using technology that you should have access to answer this. Let's look at the probability that x is equal to 5. That's going to be 6 choose 5. We already know what that one is. 0.68 to the power of 5. 0.32 to the power of 1. Okay. Probability. Let me think about this. Where is this one? I think it's in distributions, right? So you see the clear button to the left, you see this variables, and above that in yellow, you see distributions. I'm going to hit second variables to open up that distribution. Let me think about it. Binomial probability distribution. I think it's 0, right? Let's hit 0. I got to think about what the things are. So in we have 6 trials. Probability of success is 68%, and we want the probability that x is equal to 5. Let's test it out in the previous. Let's do that x is equal to 4, and we should get that same decimal. 32, 84, 18, right? So now we can just copy that. So I'm going to recall that last one. And instead of x being 4, let me check one more. Let's do an x is equal to 3, and we should get 20, 60, 66. 20, 60, 66. See, so all the stuff we were doing by hand, you see it right there. You can just type in your conditions, and it'll spit out binomial. So the binomial probability distribution function. So for the last two, I'm just going to go ahead and use this. So then I'm going to recall this. Again, the location of this, let's do this from scratch one more time. So that you see the clear button on the right-hand side of the calculator. To the left, it says VARS. I want above that where it says distribution, I'm going to hit second VARS. And then I think it was 0, binomial probability distribution. So I'm going to hit 0. That's where that was located in this calculator. Now, all calculators can't do that. That's why I showed that progression. You have to use what you have access to. Okay. So, again, we have 6 trials, and the probability of success, I need a comma. Probability of success is 68%, and we want the probability that x is equal to 5 in this case. Okay. So then this is going to be approximately 27, 91, 55. Okay. And then I'm just going to quickly do the probability that x is equal to 6. That's going to be 6 choose 6. That's 0.68. Do these right? Yeah, I think this is fine. To the power of 6, and then we got the 0.32 to the power of 0. So this guy here is actually 1. This one is also 1. It's really just the 0.68 to the power of 6. And just to show you, first I'm going to do is 0.68 to the power of 6. I'm saying that this should be the answer, so I'm going to go ahead and write that down. So this should be approximately equal to 09. Let's do 8867. All right, approximately. So then just to test out our shortcut that we just found, we want the probability that x is equal to 6, and we should get the same decimal. Okay. So then one more step to get the probability distribution function. We just put all this together in a table. All right. So we're going to have our x's, which could be 0 or 1 or 2, 3, 4, 5, and 6. And we want their probabilities next to them, the corresponding probabilities. So then we want p of x. All right. So the first one we got was this one. Let's just copy. And I'm going to paste. So there's that one. Let's put it like this. And let's move you over. We don't need all those decimals. Oh, and we don't need the calculator anymore either. I'm going to leave it for now. Let's go ahead and get a copy of when it was 1. It's here. Let's copy. And let's paste. And then 2 is here. Let's copy. Let's paste. And then 3 is here. Let's copy. And paste. Okay, so you saw a progression in the way we were generating these numbers. First we did them by hand. Then I showed you a shortcut for permutation and combination. Then I showed you a shortcut if you have like a Texas Instrument calculator, at least a TI-84. Okay, number 5 was this one. Let's undo, or just paste it. Just cut it. Paste that there, and also paste it here. That's fine. And then number 6 is here. Let's copy and paste. Okay, and the last two we used a quick method to generate these. So this was the PDF that we got. Okay. And let me actually get a copy of this because I want to compare it to, oops, I want to compare it to theirs. Let's copy. So you can see where they did all of this. They did this at 3 decimal places, which is fine. And I want to just do a side by side. I like mine to be here. Okay. So notice 0.001, 014, 073, 206, 328, 279, 099. Awesome sauce. And the sum, notice that the sum of the probabilities, notice that each probability is between 0 and 1, and the sum of the probabilities, they all add up to 1. That was an adventure. Okay, that was a lot of fun. Hopefully you had some fun there. Okay, let's keep it moving. So a survey found that 26% of U.S. adults believe there is no difference between secured and unsecured wireless networks. A secured network uses barriers such as firewalls and passwords to protect information. An unsecured network does not. We randomly select 100 adults. What's the probability exactly 35 of the adults believe there is no difference between secured and unsecured networks? Use technology to find the probability. Okay. If we're going to use the technology, so yeah, let's just do this then. We're going to do the same thing we just did. So let's think about this. How many trials are we doing? 100 adults, so this was repeated 100 times. What's the outcome of each trial? Oh, wait a minute. Yeah. What's the probability exactly? 35 adults believe there is no difference. All right. So either they believe there's a difference or they believe there is no difference. So the probability of success, there is no difference, right? 26%. So probability of success is 26%. That means the probability of failure, if that were 30, is 74 in this case. 74%. And then in this case, we want X to be equal to 35 because we want exactly 35 adults. All right. So we can actually just do what we just did, the shortcut that we just did. Let me go back. I need this one. Okay. Need you over here. So we can just call in that probability distribution function. I'm just going to hit second and recall. Okay. So how many trials? Let me see. Our n is 100. So I'm going to just type 100, comma. The probability of success in this case is 26%, so 0.26. And then we want x to be exactly 35. I'm going to hit enter. And so with these conditions, we get approximately, well, you see the number there. So you see it in the 84 plus, 01157. Yeah, they got the same thing. All right, 84. Okay. You can also do this in Excel. Okay. All right, we're going to let that be. So we just did that one. Okay. So from these displays, we can see that the probability that exactly 35 adults believe there is no difference between secured and unsecured is about, what, 1%. Because 1% is less than 5%, this can be considered an unusual event. Okay, this event is unusual. Okay, keeping it moving. So a survey found that 17% of U.S. adults say that Google News is a major source of news for them. We ran to select 4 adults and asked whether or not Google News is a major source of news. Find the probability exactly 2 of them say yes, at least 2 of them say yes, and 3 fewer than 2 of them say yes. Okay. So let's do our PDF. Let's do the entire PDF like we did a moment ago earlier. So let me do, is that the right one? That needs to be this one, right? Yeah, let's add a page here. Okay. Let's start by doing the PDF, probability distribution function. Let's see. So if this is a binomial, what's our n going to be? How many trials are we doing? We're going to select 4 adults, so our n would be 4. What's the probability of success? The survey found that says that Google is a major source. So probability of success is 17%. That means the probability of failure, if that were 20, that's 83%. Okay. And then the random variable x can take on the form, what, 0 through 4? X could be, we could have 0 people say yes, or 1, or 2, or 3, or 4. Okay. So let's do the binomial probability distribution function. So we want to say each x, again, where x can be 0 or 1 or 2 or 3 or 4. Those are the possible outcomes where somebody could say yes to this. And then let's find the probability of each one. I'm just going to use my technology. Okay. So no, why does that keep doing that? Okay, and let's bring you over here. All right, so I'm gonna go to variables. No. Math, probability. I think it was number 0. Oh, because you're not showing, you're not gonna select it. Oh, it's because it's not the right one. What's I looking for? Oh, distribution. Okay, I see it. Let's go here. And now if I hit 0, there we go. So if our n is 4, probability of success is 17%, and we want the probability of x being equal to 0. So that probability is, let's do 47, 46. 47, 46, okay, approximately. So then let's do when x is 1. Approximately, let's do 38, 88. 38, 88. Let's do when x is 2. 1195. Okay. 1195. Let's do when x is 3. See how quickly we're doing these versus when we're doing them by hand? 63, 63, and then let's do an x is 4. Okay, oh, -4, right? So 1, 2, 3, 8. Okay, that's fine. All right, what's the time? Awesome sauce. Okay, so then for the first question, find the probability exactly 2 of them respond yes. So for the first one, we want the probability that x is equal to 2. So we see here, that's going to be approximately 0.1195. That's the first answer that we got. Style, let's do it like this, right? Okay. The second question asks, at least 2 of them respond yes. So we want the probability at least 2. X is greater than or equal to 2, right? Okay. So this is going to be the probability that what? X is equal to what? 2 or 3 or 4, right? Okay. So this is going to be the same as the probability x equals 2 plus the probability that x equals 3 plus the probability that x equals 4. So then that's going to be the 1195 plus 0163 plus 0008. Okay. So let's just add those up here, I guess. I think I want to do it myself. 8 and 8 is 16. Carry the 1. 10, 16, carry the 1. 2, 3. And then a 1. And this is it. I'm going to go with this. I'll check it in a moment. I don't like that. Okay. And then the third question, fewer than 2 of them responded yes. So the third one is, we want the probability that x is less than 2. So this is going to be this, what? The probability that x is 0 plus the probability that x is 1, right? Or we could just say the probability, or we can use the complement rule. Since we just found the probability that x is greater than or equal to 2, if we want strictly less than 2, we could say 1 minus the probability that x is greater than or equal to 2, right? So we can basically just say 1 minus that 1366 we just found. 10 minus 6 is a 4. 9 minus 6 is 3. 9 minus 3 is a 6. And I think it's an 8. I'm just doing my mental math, just trying my mental math. Let me think about this. But we can use calculators. I'm just kind of testing myself. Okay. Let's see how do we do with these results. So the first one we got was 1195. Okay, 1195 is fine because we rounded that one, so that's fine. For number 2, we got 1366. 1366, yes, it rounds to that one. And then the last one we got 86 or 863. 863, you see it there. Whoop, 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 whoop. Oh, all right. Okay, moving along. 10 slides to go. I'm gonna get rid of the calculator. All right. Moving along. So in this example, it says about 10% of workers aged 16 years and older in the U.S. commute to their jobs by carpooling. We ran into like 8 workers. What's the probability exactly 4 of them carpool? Use a table to find the probability. That table's in the back. I'm going to leave this one as an exercise. So let's just look and see. So again, our binomial n is 8, probability of success is 10%, and x is equal to 4. So this is a portion of table 2 is shown. You see the n here, right? With the corresponding probability. So our n is 8, and we want x to be 4, and then the probability of success is 10%. So then with those conditions, that probability is 0.5%, or 0.005. Okay, we're gonna let that be. 62% of cancer survivors are age 65 or older. We run and select 6 cancer survivors and ask them whether they are 65 years or older. We ask to construct the probability distribution from the random variable x, then graph the distribution. So I mean, we're pretty much doing the same thing here. We're taking each x, finding their probability. I think this is the last one. I'll go ahead and do this one by hand. Don't show too much. Okay, cool. So I'm going to add a page. I'll go ahead and work this one out. That's why I was pausing or hesitating. I was deciding if I was going to write this one out or not. So I'll go ahead and do it since we have all these shortcuts, right? So let's construct the probability distribution table or function. So we're going to have each x possible outcomes. So we could have 0 say yes, or 1, or 2, or 3, or 4, or 5, or 6. 6 could say yes. Okay. And then if we find the probability of each, I think they've just been going to like 3 decimal places. Okay. So we're going to use our calculator. Okay. So let's see, the number of trials, we have 6 trials with a probability of success of 62%. And we want, for the first one, x to be 0, 0.003. Then we want for x to be 1, 0.029, 029. And then for x to be 2, 0.12. Then for x to be 3, 0.262. These are all approximations. And then when x is 4, 0.320. When x is 5, 0.209. And then when x is 6, so it's at 57, 0.57. Nope, 0.57. What am I writing it there? Okay. All right. Oh, we're asked to graph, right? Okay, so they're the probabilities. Let's go ahead and confirm that these add up to 1. Notice that these are all between 0 and 1. Let's quickly confirm that these add up to 1. So let's do 0.003 plus 029 plus 112 plus 262 plus 32 plus 209 plus 057. So they do add up to 1. And then, so to construct to graph this, let's see, x's can go from 0 to 6, and then the y's, the highest looks like it's about 30, let's go to 35. Let's Let's go to 35%. All right. So I'm gonna let my origin be like about, I don't need the calculator anymore. Okay. So I'm gonna let my origin be about here. We're gonna go this way. So let's go 1, 2, let me think about it. This will be fine. 1, 2, 3, 4, 5. 1, let's see, 1, 2, 3, 4, 5, 6, 7. Do a little bit different, okay? And then we need to get up to 35. Let me see if I go 5, 10, 15, 20, 25, 30, 35. Okay. So these are going to be, what do the x's represent? I'll just say that this is our x, and this is going to be our p of x over here, right? This needs to be 0, 1, 2, 3, 4, 5, 6. Why does it look weird? We don't really need the 7th, but that's fine. And then I need these to go, we're going up to 35. So this is 5%, 10, 15, 20, 25, 30, 35%, right? I'm going to graph these, what I would like. I guess I want a different color. Let's do this color. Okay. So the 0, let's start with having a rectangle. I'm just drawing a rectangle for right now. Nope, that's not a rectangle. Let's try that again. I'm just drawing a rectangle. Cool. Okay, so 0 goes up to 3%. So it's like way down here. That's 2.5. That's not 3%. That's like 0%. It's really, really low. So that's something like this. Probably even lower than that. Okay, that's fine. So let me draw the next rectangle. Okay, that's fine. So then when x is 1, that one is 3%. That one is 3%. So if that's 2.5, 3% is about there. Okay. The next one is what, 12%? So that one comes up to about here. So that's 10, that's 12.5, so it's about there. Okay. 3 is about 26%. So it comes up to about here. Okay. So that's 27. It's like somewhere about there. Okay. 4 goes up to 32. So then 32 is about there. Cool. Okay. So if that's what, 32.5, so about there. And then 5, so about 21%. So it's about there. So 5, this is 20, this is 22.5, so about there. And then 6 goes up to about 6%. No. That was not behaving proper. Okay, we said this one goes up to, if that's 5, that's 7, so about there. Okay, and then what I'm gonna do, I just want to fill those in. That's totally not a rectangle. Style, I wanted to fill with this color. Right. Copy, paste. That's fine. That's exactly what I want. I'm just being artsy fartsy. Copy. Just having a little fun. Just filling these with some color, that's all. Speaking of color, anybody ever seen the movie Pleasantville? That's an interesting movie. Some of my favorite movies are Pleasantville, The Truman Show. I'm a little bit of a conspiracy theorist, just a little bit. I mean, I think it's important to be informed, but at the end of the day, you know, if you can't do anything about it, you just do what you can. I personally like to know. Some people don't want to know, and I get it. You know, everybody has their path to walk, their cross to bear. I like to know. It gives me a little insight, and it helps me with positioning. It helps me like when I'm in the know, then one, I'm able to process situations and events better. I find myself being in the right place at the right time. I dodge a lot of stuff just by positioning. Not that I'm fast or anything. I just pay attention and I take notes and I take things serious and I make a decision for myself. I'm not a fan of somebody just telling me something and I blindly accept it because people lie. And so it's like if you don't make a decision for yourself, if you don't stand for something, you'll fall for anything, right? So that's why, you know, just me being Piscean, like I'm just naturally an empath, I'm naturally intuitive and I don't ignore it. I take it serious. I don't I don't necessarily automatically react. It just my antenna goes off and I'm like, wait a minute. And I just sit and I kind of watch and I'll take notes. And I mean, I've tried, you know, I'm not 100%. I'm a spiritual being having a human experience like everybody else, or I'm energy taking on the form of a human like everybody else. But you know, we all do the best that we can and keep it moving. Okay. Oof. This has been a fun lecture. I'm having so much fun. Can't you tell by my excitement by my level of elation, how excited I am? Anyway, okay, so let's see how do we do. Okay, so we got that PDF on the left with this graph. Let's go like this, paper. Let's get rid of all these lines. Okay, so we did all this by hand. I would like these at least to be a little bit more in sync as far as the size and the style. Okay, this looks better. All right, so let's see how do we do. Ow, 57. Okay, these look good. And then you see theirs versus ours. That's so much fun when I did this. You literally saw me just do these by hand and compare it to theirs. All right, nearly the same. Okay, so for the histogram, we can see that it would be unusual for none or only one of the survivors to be aged 65 years or older because both probabilities are less than 5%. So the unusual events are 0 and 1. Okay. Oh, okay. So for the binomial probability distribution function, the mean, variance, and standard deviation are given as such. So for a binomial probability distribution function, the average is going to be n times p. The variance is going to be npq, and the standard deviation is going to be the square root of the variance. Okay. In Pittsburgh, Pennsylvania, about 56% of the days in the year are cloudy. Find the average, variance, and standard deviation for the number of cloudy days during the month of June. Interpret the results and determine any unusual values. So I'm just going to use what's already typed here. So our n is 30. The month of June, right? So June has 30 days in it. The probability of it being cloudy is 56%, and the probability of it not being cloudy is 44%. So we just said for the binomial distribution, the average is going to be n times p. So basically this times this, we get this. The variance is going to be n times p times q. So n pq, and we get this. And the standard deviation is 2.7. So then on average, there are 16.8 cloudy days during the month of June. The standard deviation is 2.7 days. The values that are more than 2 standard deviations from the average are considered unusual. 2 standard deviations, right? So if this is the average, so a June with 11 cloudy days or less would be considered to be unusual, and a June with 23 cloudy days or more would also be considered to be unusual. Okay. And that actually brings us to the end of these notes. Okay. Well, that was fun. I don't know about you all, but went on a little adventure. Uh, okay. So again, as you kind of go through this material, write your questions down. You have to reach out to me, and I'm just available if you have questions. Main points for this week: Exam 2 is loaded on Pearson. Okay, so I'm trying to give you a little bit of extra time to work on that. You get limited attempts until this Saturday. It's due this Saturday night at 11:59 p.m. You can actually work on it past the deadline, but then there'll be a late penalty. And then also on Moodle, there's a participation and honesty quiz that we need to do. Okay. So on that note, we're actually going to end this session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.